Hello mathematicians, we're now going to have a look at finding the areas of compound regions. And compound regions are simply ones which involve more than one curve. So if areas are bound by different curves over the region, then we really can't do this without sketching the curve. Otherwise we're running the risk of getting the wrong areas. So what we need to do is to look at how the area can be broken up as the sum of separate integrals. So if we look at these curves down below, if we look at part A, when we look at these two curves, they obviously are both parabolas. They intersect, for what it's worth, on the y-axis. And when we go to find that area, then remembering that all we can do with our integral is find the area between a curve and the axis over a certain range, how can we break this particular integral up? So what we're going to need to do is to break it up so that the area that we want is the integral from -2 to 0, so from here to here, of this curve, so that's x minus 2 squared, and remember the dx has to go with the integral sign, plus we want the area under this curve, x plus 2 squared, between 0 and 2. And we simply add those two integrals together. Now I'm not going to do those integrals, but we should know that, for example, the first one, we add 1 to the power, so that will be x minus 2 raised to the 3, divide by the 3, and divide also by the differential of the bracket. And remember that that's a technique that we can't use if the power of the x in here is any greater than 1. Now for our second example, it's very similar. It's just that the curves don't intersect on the y-axis. So when we go to find this area, then the total area is the area from 0 to the point where they do intersect, which is this x value. So 0 to 3 on 2 of x squared, and from 3 on 2 to 3 of our other curve, x minus 3 squared. And again, I won't do the integrals, but we just carry on and do the integration. Now, if we have an area which is actually bound by two curves, then if we want the area between the two curves, that area is given by the integral from A to B, which are the 2 points where they intersect each other, of one function minus the other function. Now, which function minus which function? Well, if the curve fx is greater than or equal to, so it's simply higher than g of x, then this is what we do. If g of x is higher than f of x, then we swap these around. And if we really don't know, then we may have to end up simply taking a guess and then find the absolute value of the result. But we'll always subtract one function from the other function. And the guesswork is taken out if we can actually do the sketch. So let's have a look at GeoGebra. So here we have two curves. We have our parabola x squared minus 4x plus 2, our straight line y equals mx plus b, and b is controlled by this slider here. And when we find the area between the two curves, if we look at the formula down here, if we take the integral from 0.44 to 4.56, so the two x values, of the top curve minus the parabola, the lower curve, we get 11.68. If we had no idea which one was the top, and we went from one point of intersection to the other, and we said the parabola minus a straight line, we get the same magnitude of answer, but with a negative sign. So the 11.68 is the area. Area is a dimensionless quantity. And we get that straight up by our first calculation. So the fact that some of this area is positive and some is negative is taken into account by putting our limits in. But whether it's a minus sign or a plus sign overall just depends on which curve we choose as the top and which one is the bottom. So if we have the sketch, do it with the top minus the bottom. If we don't have a sketch, or if we're unsure, then just remember to take the absolute value at the end. So if I took that line and slid it up, for example, we see that the area increases. I take it down, so I change the proportion of positive and negative. So you can see pretty clearly that the amount of shading here in the negative area is more than this bit, but the area between the two curves, the dimensionless quantity, still comes out to be 2.96. So it should always be a positive value. Now notice that this technique of simply subtracting one integral from the other between their points of intersection is fine if the curves only cross each other, if the curves only intersect at a pair of points. But if the curves cross each other at different points, we need to bring into account separate integrals. Otherwise, we will have areas or regions where different curves are on top, and so we'll possibly cancel each other out to some extent. So let's have a look at GeoGebra to see how this operates. So if we look at these curves, our straight line and this cubic, we can see that in some places the cubic is higher than the straight line, and in other places it's lower. If we simply took the integral from minus 2.3 up to 3.6 as one integral, then that would give us that the overall area between the curves, if we took one curve minus the other curve, is 33.8. However, if we take the areas separately, so if we took the area from A to B, we get 6.2. So this is where it would be the cubic curve minus the straight line. And then if we take the area from B to C, which would be the straight line minus the cubic, then altogether that gives us the total area between the curves as 46.2, as opposed to the 33.8 that we would get if we didn't take into account that the curves changed in terms of one being higher than the other. So let's take a look at this example. So first part says, by solving the equation simultaneously, show that these curves intersect at these points. So that's just straight solution of equations simultaneously, setting them equal to each other, and we verify that fact. Then sketch the curves on the same diagram, shade the region enclosed between them. So this is so that we can start to get an idea of the problem. So when we do that, this is our parabola, this was our straight line, y equals x plus 6, cutting through at 6. We can see the area in between them. So we can see that the straight line is higher than the parabola over the region we're interested in. So part C, show that this region has an area given by this, so the integral from minus 1 to 2 of the top curve minus the bottom curve, and then if we work on this algebraically, that becomes simply this, and then evaluate the integral. So when we evaluate the integral, we can see that essentially we're saying that that region under the curve is the area under the straight line, which is given by that, minus the area under the parabola, which is given by that. Putting them together, we get the result shown up above, which we're aiming to get. Simplifying the algebra, we get that. We then do the integration according to our rules. So this is the result of integrating between these limits. Plug the limits in, and we get that minus that, which gives us 3 1/6 as the answer. So the most important thing about this video is for you to take the ideas which we've looked at and reduce them to a concise and precise mathematical description of what you've learnt in this particular video. So that's your challenge, and it's going to be your challenge on every video from here on out. What, in simplest and most concise terms, is the big idea from this particular video, so that once you understand that idea, you can apply it to a range of different situations.